Hello, my name is Peter, and I will introduce our work on differentiable SLAM-net. Visual SLAM, simultaneous localization and mapping, is an unsolved problem. While existing solutions work well in benchmark datasets, they can fail completely when used, for example, for robot navigation, because the robot can rotate quickly, face featureless walls, its camera frame rate might be low, and images can be noisy. We introduced the differentiable SLAM-net that encodes a complete model-based SLAM algorithm in a differentiable computation graph and trains learnable model components end-to-end, from image input to pose output. We can look at SLAM-net from two perspectives. First, SLAM-net can be understood as a model-based SLAM approach, where the model components are neural networks and the SLAM algorithm is differentiable. Because of the differentiability, we can train everything end-to-end, backpropagating gradients through the algorithmic computation. The benefit is that all model components, like feature extractors or map representation, are all learned to optimize the final task objective. We can also understand SLAM-net as just a large neural network that has inductive bias in the form of the built-in algorithm. The idea could be applied to many SLAM algorithms, but in this work, we use a particle filter-based algorithm called FastSLAM and learn neural networks for its mapping, transition, and observation models. Our inputs are RGB or RGB-D images, and outputs are 2D pose estimates, including orientation. This is a detailed architecture. The core is a set of k-weighted particles, where each particle is a hypothesis for the robot trajectory, and the particle weight represents how likely a hypothesis is. With each new observation, particle trajectories are extended with samples from a transition model, which is a learned CNN estimating relative motion between frames. Another CNN, called a mapping model, predicts a local map, and the local map is added to a collection. These local maps are learned latent features organized into a 2D grid, and optionally they can be supervised with occupancy grids as well. Finally, particle weights are updated with an observation model that estimates whether local maps could be consistently combined together if the particle trajectory was correct. Our observation model is a learned CNN that learns pairwise comparisons of appropriately transformed local maps. The output is the weighted sum of the particle trajectories and optionally a global occupancy grid map constructed from local maps. To make the complete architecture differentiable, in the transition update we use the reparameterization trick, and in the observation model we use spatial transformers. We evaluated SLAM-net both for pose estimation and downstream navigation in previously unseen environments. Training data is collected in the habitat simulator, which has real-world indoor image data. We then did testing in new environments that were not in the training set. We compared with both learning-based and model-based alternatives. First, SLAM-net outperformed the learned visual odometry method, possibly because it has useful inductive bias. And here we are measuring success rate, where success is defined as the pose error being under a certain threshold. SLAM-net also outperformed two model-based algorithms, FastSLAM and ORB-SLAM. For FastSLAM, the algorithm itself is actually exactly the same as for SLAM-net. The only difference are the model components. SLAM-net learned more models that are more effective because all the feature extractors, the map representation, and everything else are optimized together for the final objective. ORB-SLAM is actually a more popular method, but it performed really poorly here. To understand why, we tried it in an idealized setting with no noise and high frame rate, where it actually performed well. A possible explanation is that ORB-SLAM relies on tracking temporally consistent visual features, which fails with our noisy robot navigation data. When we tried using more difficult trajectories or RGB-only input, we found that the benefit of SLAM-net was even larger. We also tried SLAM-net for robot navigation by adding it to a standard navigation pipeline using an A*-like path planner and a simple motion controller. This is our agent successfully navigating in a previously unseen environment.
This navigation approach achieved state-of-the-art for the CVPR 2020 Habitat Challenge, significantly improving success rates on a closed testset. For future work, we are excited about new differentiable SLAM algorithms, as well as the potential of learning latent map representations for downstream decision making. Thank you.